Hey guys, so in this week we're going to begin chapter 4. Chapter 4 is about the first law of thermodynamics, specifically on closed systems. Okay, so closed systems, you remember, are systems that have physical boundaries, and in closed system mass is fixed. Okay, but before we move forward with the analysis of the first law of thermodynamics, there's something that you need to learn, which is a moving boundary work. Okay, and I'm going to tell you what that is and how it fits into the entire energy balance equation. So what you've learned before, energy balance equation, energy going into the system minus energy leaving the system equals to change in the total energy of the system. Okay, and this applies to closed system, which we are only going to study two, which is a tank and a piston cylinder. A tank has fixed mass, fixed volume, and a piston cylinder has fixed mass but changeable volume, because this piston head is allowed to move up and down. Okay, so let's go back to this equation. So for on the left side, E in and E out are the only two, there are two ways of energy transfer, which is heat and work. Okay, there are only two methods of energy going in or leaving the system. In or out can only be in Q or W. So it becomes work in minus work out plus Q in minus Q out equals 2. Okay, on the right side, this is the total change in energy of the system. Okay, what's changing inside here? So there are three items that we can check. One is the internal energy of the system. The other two are the macroscopic, okay, the ones that you can see, KE and PE. So where does boundary work, which is the name of the chapter, where does it fit into this whole equation? So we have work here. You have seen spring work. Okay, you have seen shaft work. You have seen, what is this? Electrical work. Okay, so we are going to see another type of work, which is boundary work. Okay, why it has its own subtopic is because you have not seen it before. Okay, EE you've seen before. You've seen in EE subject. Shaft you can see in MOM, you can see in machine design and all that. Spring you have seen in physics. Okay, so boundary work is special, so we have to discuss it first. And then we will bring this whole information into the energy balance equation again, which is the major part of chapter 4. Okay, so don't forget this main equation. Now let's talk about boundary work. By the name of it, moving boundary work, that means it's a work, okay, it's very straightforward. It's a work done by a boundary that is moving. Very simple. So when will you have a moving boundary? When you have a piston. Okay, you have to have a piston in order to have a moving boundary work. And not only that, the piston head actually has to move. Okay, so the work associated with a moving boundary is called boundary work. If the piston head is not moving, then there's no work, there's no boundary work. Okay, so in short, moving boundary work is associated to the expansion and compression of a piston. Okay, I'm not going to explain this yet, quasi-equilibrium, maybe in class. So what's happening here actually? Who is doing the work? How come the piston can move? So what's happening is the gas inside, let's say it's expanding. Okay, let's say the gas inside, you heat it up, just like in your test 1 question. The gas is heated, it expands. Okay, the gas is trying to push out. And because the piston is there, it can push the piston up. So that's how the pressure remains constant, remember? P will remain constant. So the gas is pushing up, and there's this area that it's acting on, which is the cross-section area of the piston, and this will result in a force. Okay, and this force will be moving the piston by a distance ds. That's how you get work, force times distance. Alright, so let's look at this. Boundary work is pressure times change in volume. So how do we get this equation? Okay, where did this equation came from? So boundary work, we start here. Boundary work is force times distance. This is any work actually. F times distance is any work. And force is pressure times area, and then pressure is still here. Okay, pressure. Area times length. Area times length, you get volume. So that's how you can relate. Boundary work is a P times change in volume. So to calculate it accurately, you have to have this integration. Okay, boundary work is an integration from point 1 to point 2 of pressure with respect to volume. Okay, don't panic yet. You don't really have to do the integration. We'll see. Okay, now the unit is of course the same unit that we have been using because it's a type of work, therefore it's kilojoules. To establish the sign, whether it's negative or positive, normally if it's positive boundary work, it's expanding. Okay, so easy. If the volume is increasing, then it's positive boundary work. If the volume is decreasing, compression, then it's negative boundary work. Right? Now, the same equation. So to integrate this, we need the equation for P. Okay, you actually need a function of P in order to solve for boundary work. And this is the PV diagram. You can see the process happening on the PV diagram. So this is the piston. Let's say the pressure is inside here and it's moving. Yeah, it's expanding. So what's happening on the PV diagram is the pressure will actually reduce while the volume is increasing. So you might be wondering, why does the pressure reduce? The pressure is supposed to be constant, right? But there are cases, okay, specifically for ideal gas. You're going to see it in the next video. Okay, so you can get a reduction in pressure even though it's a piston. Alright, but something else has to be constant. So we're going to see that. But what I want to show you here is the boundary work is actually the area under this curve. So for the area for this section, how much work is done to move this blue section is equals to this area, because this area is actually P times V. You just calculate the area under the curve. Okay, so apart from the equation, the area under the process curve on the PV diagram also represents boundary work. Alright, so you've learned two things now, the equation and that area, this one. Okay, area under the curve is also. Okay, so what we have here is the PV diagram, and you have three paths. Remember, path is a description to complete the process. Okay, which way does the process take? Because it starts at the same point and it ends at the same point. So if you take different routes to get there, the result will be a little bit different, even though you get at the same point. Okay, so what is the effect here? You can see that the boundary work done depends on the path as well as the end state. So yes, we are starting at the same point and we are ending up at the same point. But because boundary work is area under the curve, obviously for path C, this will be the area, right? The smallest area. So that's why the work is the smallest here. If you consider path B, you have to add whatever work you get here with this region. Let's get 8. And then for A, again, even more. Okay, you get 10 kilojoules. So boundary work depends on the path, not only the initial and final state. So you have to see, is a process happening at constant pressure or constant temperature? What is happening? Okay, we have to know that. Next, alright, the net work done. So you know that when you have a cycle, for example, think about your car engine. Okay, it's a cyclic device. Okay, you don't have to start it 200 times just to drive to the shop. Once you turn it on, and then it's working in a cycle. You know that, right? Compression and expansion of the piston cylinders. So how that works is, during compression, the system goes from, this is point 1, you see, bigger volume, it goes to point 2, smaller volume. So that's compression. And then it expands again, but using a different path. So when it goes here, this amount of work is involved. This is negative because it's becoming smaller, right? Compression, so minus. And then when it expands, you get a positive boundary work. So the net work will be adding these two up. Okay, so that's how generally you get the net work from cyclic devices. Okay, so I told you that you don't have to do the integration. So in the next video, we're going to cover these 3 different cases that could simplify things. All right.